finish section 14.1, and this is about mass centers and systems of particles. So if we take a look, the problem that I would like to work for you is, I'm going to have to widen this out a little bit. There we go. I'm going to put in your homework assignments for you to do 14, 19, and 20, which go together. They're more like one big problem. And then I'm going to work problem 14.24. And this is a very good problem because it really emphasizes some of these considerations of how the vectors work on this type of the problem. All right. And I like this problem also because we really get into the math, so that if you're more comfortable with the math, then you can work this out in a purely mathematical way based on the principle of conservation of momentum. All right, so let's take a look and read through the problem. It says we have a 6 kilogram shell, big shell. It is moving with a velocity of 12 meters per second I minus 9 meters per second J minus 360 meters per second K, and it explodes here at point D in front of a wall. All right? When it explodes, D, the 6 kilogram, breaks into 3 fragments, which are A, B, and C. So the mass of C mass of A is 3 kilograms, B is 2 kilograms, and C is 1 kilogram. All right? Now, the first thing to note is that conservation of mass requires that these 3 add up to 6. If they didn't, we would have another piece that we would have to account for. That would be mean at this point. Your authors would not do that to you, but that we would have to account for that. So it says, knowing that the fragments hit the vertical wall at the points indicated, determine the speed of each fragment immediately after the explosion. And we get to ignore gravity in this problem. All right, so basically what we're saying is there's going to be a velocity of A immediately after the explosion, a velocity of B immediately after the explosion, and a velocity of C immediately after the explosion. And we don't know what any of those things are. But we do know that in each case, each of those vectors can be expressed as the magnitude times the lambda from point D to the point where it hits the wall. In other words, we're saying that the velocity's trajectory, the fragment's trajectory, is going to be from point D to point A, from point D to point B, and from D to point C. Okay? So if we can find that lambda from D to A, we can express this as a vector. Okay? Okay? So in terms of math, the first thing we need to do is define these vectors. But what is the principle that we're talking about? Well, if you think about that, a shell exploding is a good application for conservation of momentum, which says that the momentum before, in other words, the momentum of this shell, we're calling it L, sorry, L before the explosion, I, is going to equal L afterward. But we know that afterward we have a summation. We also know that these things are vectors, so that L1 is md, the whole shell, times the velocity vector before it hits. okay, before it explodes rather. And that afterward, we're going to have the mass of A times the velocity vector A plus the mass of B times the velocity vector of B plus the mass of C times the velocity vector of C. And what we're asked to find in this problem is the magnitudes of those velocities. So what that means for us is that we have to work out the math. We do not have, we do have the masses of each of these. We do not have the velocities, and these are actually the unknowns that we're looking for in this problem. So that means that in order to work out this problem, we're going to have to find our lambdas, and then we're going to have to break this equation up into the three directions, into I, j, and k components, or x, y, and z components. Okay, so then we could say in the x direction, the mass of d times the velocity of d in the x direction is equal to the mass of A times the velocity of A in the x direction. I'm not going to write this 9 times, please don't worry about that. Mass of B times velocity of B in the x direction plus the mass of C times velocity of C in the x direction, and similarly for the y and x, y, z directions. All right? So now at this point we get to do the math. The first thing we need to do before we can write our velocities as vectors is to find our lambdas along each of those trajectories. So in order to find lambda dA, we first have to write the vector dA just in terms of components, and we have all of that information here. So from D to A in the x direction, we move to the left 1.5 meters. So that is minus 1.5 meters I. In the j direction, we remain flat, so it's 0 j. And in the z direction, we go back into the page 4 meters. So that's minus 4k, and that's in meters. Okay, I'm going to do the same thing for dB, since I'm kind of on a roll, and dC. So from D to B, in the x direction, we move to the right 4 meters. In the y direction, we move up 2 meters. Oops, can't see that. I don't know if you can see it anyway, but from D to B, there we go, we move to the right 4 meters, up 2 meters, and in the z direction, we're still hitting the same wall, so that's negative 4 meters in the k direction, like that. All right? And then last but not least, from D to C, in the x direction, we're right on the y-axis, so it's 0 in the x direction. In the y direction, we're moving down 3 meters. And in the z direction, we're going back into the board that same 4 meters. So it's minus 4k meters. All right. So now we're going to do a little vector math. To find lambda, after we write our vectors, we need to find the length of each of those vectors using the Pythagorean theorem. And if you remember, the Pythagorean theorem, when we square a number, negative 1.5 is still a positive, so I've just dropped my signs for convenience. So, clear. If I take 1.5 squared and add it to 4 squared, which is 16, take the square root of that number, I will get the length of dA, which is 4.27 meters. For dB, again, get the length, 4 squared plus 2 squared plus 4 squared. That's 16 16 plus 16 is 32. 32 plus 4 is 36. So the length of that is exactly 6 meters. And then DC, I need to write this just so I don't get mixed up. There we go. DC, square root of 3 squared plus 4 squared, 9 plus 16, very famous square root of 25, 5 meters, right? All right, so then the next thing we need to do is to write each of these as a unit vector along that direction. So we can say, and I'm just changing colors. Can you see this all right? If you can't see it, I'll use a different Sharpie. But let's, have a green Sharpie. Let me do that one. That'll be better. Okay. So VA times DA is equal to VA, magnitude, times the vector negative 1.5 over 4.27I plus 0J minus 4 over 4.27K. And VB as a vector is equal to the magnitude of VB times 4 over 6I plus 2 over 6J minus 4 over 6K. And then my velocity of C as a vector is the magnitude of velocity of C times the unit vector 0I minus 3 over 5J minus 4 over 5K. All right. So now we can write this, and we could actually, let me think. I'm just trying to think of how to organize this. Let's do it this way. Let's do it in the x direction. Let's say MD times V0x. All right? And we have our components of V0 here. So this is 6 kilograms, that's the weight of the shell, times 12 meters per second. That's all of our initial momentum. So that's going to equal the momentum from each of these 3 bits in the I direction. So we have negative 1.5 over 4.27 V sub A, moving down here, plus 4 over 6, which, yes, it reduces, but you'd be surprised how much easier it is to find your numbers again if you do it this way, times V sub B, and then the C direction, the C velocity component in the x direction is equal to 0. So that's just equal to these 2 things. So this is one equation with 2 unknowns. Let's go in the y direction. We have the same, I forgot my masses. So the mass of A is 3 kilograms, and the mass of B is 2 kilograms. So we'll simplify that in just a few minutes. In the y direction, initially we have that 6 kilograms, but our y component of velocity is negative 9 meters per second. So there's our vector momentum that we have to work with that we conserve in the y direction. And that turns out to be, let's see, VA in the y direction is 0, so there's no add there. But in the b direction, we have B, which has a mass of 2 kilograms, times 2 over 6, which is positive or negative? It's positive. Let me just look at my picture again. Yeah, it is. Times V sub B, And still in the y direction, we get C, which has a mass of 1 kilogram, times negative 3 over 5 V sub C. Okay. So we have one more equation with two unknowns, but they're not the same. Oops, you can't see that very well. Two equations, but now we have a total of 3 unknowns, so we can't solve yet, can we? All right. In the z direction, do the same thing. We take our mass of that original shell, 6 kilograms, and its velocity in the j direction is negative 360, and that's going to equal the mass of part A times the velocity component in the j direction. Okay. And then B in the j direction, which is 2 kilograms minus 4 over 6 V sub B. And last but not least, 1 times negative 4/5 V sub C. All right, now we have 3 unsimplified working equations, and we have 3 unknowns. So we know we can solve this, but we get to decide how that will be. When I look at this, these 2 equations have V sub B in common. So I would solve this in terms for V sub A in terms of V sub B, and solve this for V sub C in terms of V sub B. And then I could plug that in here and here, and then I would have one equation in V sub B only. Then I can go back and back substitute into the other equations. All right, so let's simplify the look of our work here. Now I've got everything all constructed. All right, so I'm just going to rewrite these in slightly simplified forms. 6 times 12 is 72, I believe. Yes, still. So the x direction equation says 72 is equal to, and if I take 1.5 and divide it by 4.27, I get negative, I got to multiply that by 3 because that's that mass. Okay, so 1.05 V sub A plus, then I have 2 times 4/6, which is 8/6, which is 1.5 or 1 1/3, excuse me, 1.33 V sub B. So my x direction equation just simplifies arithmetically to look like that. Y, 9 times 6, negative 54, equals 4 over 6, which is 2/3 V sub B. I'm going to keep it in decimals or I'll make myself crazy. 0.67 V sub B. And then 1 times this is minus 3/5, which is 60.6. Yep. 0.6 V sub C. And then in the z direction, 6 times 360 is negative 2160. And then I have 3 times 4, which is 12, divided by 4.27 for my coefficient of V sub A. Negative 2.81. Just be careful. Yeah, that's okay. V sub A minus 8 over 6, which is still 1.33. V sub B minus 4/5, which is 0.8. V sub C. All right, and here are my working equations. Once I have this, I can solve this for V sub A, solve this for V sub C, and plug in those values, and I can solve directly for v sub b. So I would solve this for v sub a. So I'm going to keep this on the right-hand side of the equation, v sub a. I don't know why I wrote that. So I get 72 minus 1.33 v sub b all over 1.05. Okay? And so 72 divided by 1.05 is 68.57 minus, then I have 1.33 divided by 1.05. That number is 1.27 v sub b equals v sub a. And this is what I'll use for my substitution. And I'll also backfill it when I get to that point. I don't have to go back to the beginning to then solve for v sub a. Once I have v sub b, I can plug it directly into that equation. So same thing here. Now this is a negative, so I'm going to bring v sub c over to the other side of the equation. And so I'm going to have a positive v sub c equals positive, when it comes over, 54 plus 1.67 v sub b all over the coefficient of v sub c, which is 0.6. So when I do that, I say v sub c is equal to 54 divided by 0.6, which is 90, plus 1.67 divided by 0.6. And if you have an equation solver, needless to say, this will go a lot quicker. V sub b. Okay? So there's my two substitutable values. So in the final thing, I'll take this equation. Negative 2160 equals negative 2.81 v sub a, which is itself 68.57 minus 1.27 v sub b, minus 1.33 v sub b, minus 0.8 v sub c, which is 90 plus 2.78 v sub b. All right, so what I have there is one equation and one unknown, which algebraically is a huge relief. So if I take my coefficients, 2.81, I distribute through, multiply it by 68.57. This first number is negative 192.68. And when I multiply negative times a negative, I get a positive 3.57 v sub b. And I have minus 1.33 v sub b. And when I multiply 0.8 times negative 0.8 times 99 times 8 is 72. So that's a negative 72. And I multiply 2.78. Yeah, those are both positive. That's weird. Times 0.8. And I get 2 minus 2.22 v sub b. All right, then all that's left to remain is to bring my constants to one side of the equation and consolidate my v sub b's. So I get 2160 negative. Then I'm going to add to that, let me do this, negative 2160. Then this comes over as a positive, plus 192.68. And this comes over as a positive, 72. So my constant term on the left-hand side is 1895.32. Then bring together my v sub b terms. I get positive 3.57 minus 1.33 minus 2.22. And that value is 0.02 v sub b. That looks huge. And I think I probably have an arithmetic mistake somewhere. But the process is correct. So if I take this number and divide it by that number, yeah, there's definitely an arithmetic mistake because it comes out to be negative. So I would get 1895.32 divided by 0.02 and that would be 94766 equals V sub B. Okay, I'm going to put a question mark next to that because that looks huge, but yeah, it's way too high. But anyway, so did anyone use an equation solver? What'd you get?
I still got a negative value.
Okay.
Negative 14, 18.64.
Okay, well,
14, 18, sorry, 1,014.
okay. All right, equals V sub B. All right, so somewhere in that math is an error, and it could have been when I distributed something through. So this is another thing I want to show you is when you're doing an exam, just make sure that you show me all the work, because if you just make a little mistake somewhere, you're not going to lose very much credit. So I know all of you will, but that's important. Let's go ahead and finish up the process. If V sub B were indeed this value, then we could say V sub C is equal to 90 plus 2.78 V sub B. So we could take that value, 1895, and it should be, oh, and that would be in, I did write meters per second, yeah. Okay, and it should be positive. It doesn't make any sense for it to be negative. So, so we get 1418 times 2.78, and that would be minus. So that would give me a negative 3852 meters per second. And then last but not least, V sub A would go back to this, and it would be 68.57 minus 1.27 V sub B, which is that when I'm using negative 1895. And so if you get 1895, now here you get a positive value because negative times negative, which I still don't believe, but 68.57. So that would give you a V sub A value of 2475 meters per second. Okay, so
wouldn't you be using your 9,000 or 94?
well, I did. I just liked AJ's value better. Yeah, I don't think his is right either, but I think it's less wrong than mine. So, so I would suggest on this problem. But anyway, whatever you use for V sub B would be substituted into the other equations. But in this case, there's an arithmetic mistake somewhere. Probably what I would do if I was a student working this problem, I would first check to make sure that I had all of my unit vectors correct. Okay? And then the next thing is I was a little sketchy when I put in my masses. So when I did my momentum equations, I would make sure that I put in my masses. Okay? Now, see, I would expect if you look at the velocities in the x and the y direction, the v stuff is a lot bigger, isn't it? So that's just something to think about. But there's definitely an error in the arithmetic. The process is the way that you should do it. And like I said, if you did it on a test and you came out with those errors, you would not lose much credit. But let me tell you, this is 1424. I'm going to tell you what the author's answers are, and I'll take a look here and see if I can trace back my error. The author's V sub A is 431 meters per second. V sub B is 395 meters per second. And V sub C is 528 meters per second. Okay, so let me come here and take a peek. See what, let's see, let me put this up on the screen. Now you've got that in your notes, so let's take a look at the podium PC and take a look at the math. Okay, so if I look at my unit vectors, negative 1.5 minus 4 with a length of 4.27, so R sub A, or the length, the vector dA is correct. V sub B, 4 to negative 4 with a length of 6 is also correct. And then the last one, negative 3, 4, 5. Yep. So my unit vectors, my lambdas are all correct. So that means that this part of the work is correct. This part of the work is correct. So somewhere in the clot of that arithmetic, we have a little error. So if you find it, like I said, if you're doing your homework, you don't have to exhaust yourself with that if you're going through the process correctly of setting up the vectors. But it's always nice. It's always a swell feeling to get the right answer. So I wrote the answers down so in case if you want to work through that and see it, you can. You don't have to. Sorry?
There's just one negative sign, that's all.
Where is it? Tell me.
It's negative 1.05 dA on the first equation.
Here.
Yep.
This should be a negative?
Yep.
Ah, sweetness. Very good. Thank you. So now you know. And that'll do it to you every single time. So very nice. All right, guys. So like I said, I will get. This is our last lecture for section 14.1, and I will. I'll have this posted as soon as they develop it, as soon as it processes. I do have the PowerPoints up for chapter 14, so you should be fine as far as following along. And then I will send out a poll of some sort this weekend to give you some possible times when you can have a 2-hour block to take your midterm exam. All right. And like I said, I would prefer to sit in the classroom with you guys, but if you're in a weird situation and you need me to Zoom it with you, I can do that as well. All right, you guys have a great day. We'll see you next time.